parabolas, if you wanted to call it that, and they're bounded because of the asymptotes, kind of forcing them to skim along the asymptotes. So a regular parabola gets wider. These do not. They just skim vertically around the asymptotes. And then I just wanted to look at the secant function. So here's my cosine graph, and I have some dots plotted on here. I pretty much did the same thing we talked about yesterday. So anywhere cosine has an x-intercept, the secant has an asymptote, and we'll focus on that tomorrow as well when we graph them. So I placed my asymptotes at all the x-intercept locations. And then when the secant is, or I'm sorry, the cosine is 1, the secant is also 1. When the cosine was at 1/2, the secant is at 2. And I have those points plotted on here. So just playing connect the dots, there is a parabola connecting these points, again, like a parabola shape, I guess we could say. So there are 3 full parabolas in quotes there. And then there is one at each end, and it's kind of like just a half on the one side and a half on the right side. But please make sure you are graphing those 2 pieces, even though they're half, because of the period being -2 pi to +2 pi, it doesn't complete it. But make sure you are graphing the half on the left and the half on the right to complete the full period. So this is what your secant graph should look like. So we use the cosine to create the secant, and we will do the same thing tomorrow as well. We'll actually graph cosine and sine to create secant and cosecant. So I just want to go over the questions underneath, and these questions are kind of similar to the ones you were asked about the secant. But just to talk about these, so when we're looking at the domain would go from one asymptote to the next, and because the left side of this graph, it does start at -2 pi, but we're kind of missing half of it. So you could say the domain, it's actually going to go all the way over to -5 pi over 2 to -3 pi over 2, because there is going to be an asymptote at every pi over 2 location. And then I would have -3 pi over 2 to -pi over 2, and so on. So as long as you're understanding that the asymptotes are creating the domain, that would be the one thing to kind of understand. Part B wants you to find the range. If you look at this graph, remember the range would be the vertical part of the graph. Peter, what did you get for the range of this secant graph?
I got -infinity to -1 in union with 1 to infinity.
Yeah, nice job. And those ones are in brackets because that would be the tip of that parabola shape. So they are in brackets there. Even or odd. So remember, even functions have y-axis symmetry, odd functions have original symmetry. Well, if the cosine was even, and this is created from a cosine graph, then the secant is also even. And if you look, the y-axis cuts the graph directly in half. So I have a reflection across the y-axis. So again, cosine is even, so secant is even. And then D and E, it wants the max and the min value. Technically, the max would be infinity and the min would be -infinity. But if it said a relative max, the relative max would be at +1, or I'm sorry, at -1, and the relative min would be at +1. So I probably should have worded that question a little different. But like this value right here, that's called a relative max, or I'm sorry, relative min. It's the lowest point of the curve. But really that graph goes to positive infinity, but the lowest point of that curve is a 1. So depending on how you're wording that, I should have worded that a little different. So if you had infinity there, that's fine. If you had the relative max being a -1, that would be fine as well. The period is 2 pi. Period of cosine is the same as the period of the secant. The asymptotes are every pi over 2 location. Oops. So negative 3 pi over 2, negative pi over 2, positive pi over 2, positive 3 pi over 2. Jenny, were there any x-intercepts of our secant graph?
No.
How about y-intercepts?
Yes, it was at 0, 1.
Yeah, there is a y-intercept because it does cross the y-axis at 0, 1, but no x-intercepts because the x-intercepts from the cosine are what create the asymptotes. So there is a y-intercept. And then this question wasn't on here, but we'll talk about this. There is no amplitude. And the reason there isn't an amplitude is because, again, this graph stretches to infinity or negative infinity. So there's not going to be an amplitude of a function if it stretches to infinity. And that's the same thing with tangent and cotangent. So sine and cosine have an amplitude because they have a true max. They have that top of the curve or the bottom of the curve, but it's not going beyond those values. That's why they have an amplitude. But the secant and cosecant graphs do not because they go stretch to infinity. Does anyone have questions on that?
Wouldn't the period just be pi?
So that is a good question. The full graph, it's because it corresponds directly with cosine, they are reciprocal functions. If a cosine graph goes from 0 to 2 pi, because they are reciprocals, the secant graph also goes from 0 to 2 pi. So a full graph has, in this case, we have the full parabola, and these guys here would also make a full parabola. But it has to correspond directly with cosine. And that's the same thing with the cosecant. So a full graph is actually one parabola that faces up and one parabola that faces down. So
Okay, thank you.
yeah, you're welcome. But once you have both of them, then it starts to repeat. Because they're different, it's not a true repetition until you have both the one that goes up and the one that goes down. So the period of sine correlates directly with cosecant. The period of cosine correlates directly with the secant. Good question to ask, Jenny. Other questions? All right, so we're going to go into the notes and look at tangent and cotangent today to see how we can shift them and stretch them or shrink them, I guess, depending on what we're looking at. So in your packet, this is page 37. And we are going to graph tangent and cotangent up above. We're going to skip secant and cosecant. And then we have an example of tangent and cotangent to graph with some shifts in the graph. So we're going to start first just by graphing a tangent function. And it says to graph the tangent function from negative 3 pi over 2 to positive 3 pi over 2. We're going to label the graph exactly the same way we've been labeling the graph. So if you go up 4, we're going to call that 1. And just like we have with the x-axis, we're going to count by pi over 2. This is just a general tangent graph, the most basic tangent graph. It's also called the parent function because it's just y equals tangent of x. And we're counting by pi over 2 here as we did yesterday. And it asks us to go to 3 pi over 2. And the reason we have that is so that we get a full tangent graph and we don't just have like a piece of it hanging out on the left or the right side. And I'm going to just label the other ones so that we have the labeling done. The cotangent, we're going to label from negative pi to positive pi. And then the labeling part of both of the graphs are done. Can you guys give me a thumbs up when you're done labeling? Just don't want to go too quickly. So if you're done labeling, just give me a thumbs up, please. Awesome, thank you. So tangent, we're going to focus on the asymptotes and the intercepts when we graph tangent and cotangent. So a little different than when we're graphing sine and cosine. So I'm going to travel back to the graph that we did yesterday for tangent. Ugh, there it is. And here is this wonderful graph of tangent. There are 3 periods drawn. Each time you have the same graph repeat, you have a second period. If you look at the asymptotes, we said the asymptotes yesterday were at every pi over 2 value. In the middle of the asymptotes is where we would have the x-intercepts. And that's really, we're going to focus on the asymptotes and the x-intercepts of the graph. And the intercept should always be directly in the middle of the 2 asymptotes. So when we come down here to get a general sketch, we will have asymptotes at any pi over 2 value. So I should have one at negative 3 pi over 2, since we're graphing all the way to negative 3 pi over 2. Negative pi over 2, positive pi over 2, and positive 3 pi over 2. So tangents asymptotes are always at any pi over 2 value. So we're going to sketch them in first. Again, that'll be the main thing we focus on. So to create a tangent graph, the first thing we would find would be, where are the asymptotes of the graph? Directly in the middle of every asymptote is an x-intercept. So if you look at the pair of asymptotes, the middle of them will always be the x-intercept, no matter what. So if I go to the middle of each asymptote, I would have an x-intercept in the middle of each one of those. And that is a characteristic of a tangent graph. Remember, everything is still equal distant. So the center of the asymptotes will be the x-intercept. And then the last thing that we are going to graph is in between the x-intercept and the asymptote. That angle is a pi over 4 angle. Well, the tangent of pi over 4 is 1. So I'm going to go in the middle. And I'm looking right here. I'm starting on the left. So in the middle of the intercept and the asymptote, tangent of a pi over 4 value is 1. And on the other side, it has to go down to negative 1. Tangent is an increasing function. So just scrolling back up here and looking at my tangent graph, tangent increases from left to right. So the left will have a negative 1 value, the right has a positive 1 value at every pi over 4 angle. Oops. So if I continue going in the middle, so directly in the middle is a pi over 4 angle in between 0 and pi over 2. I would have a value at positive 1, and I have a value at negative 1. And again, directly in the middle, a value at positive 1 and a value at negative 1. If you want to put a little tick mark there in the middle, we can do that as well to kind of represent that angle. So tangent increases from left to right. When you connect these points, try and make it curved. It is not a straight line. It does have a curve in it. It's kind of like an S curve or that x cubed curve. So if you start at the x-intercept, connect up, go toward the asymptote, connect down, go toward the asymptote. But make it as curved as possible, not a straight line. So I like to start in the middle and I just connect up and I connect down, and that helps me get a better curve of the graph. So I still have points in this graph. I have 3 points and 2 asymptotes. So in a sense, there's still 5 important values that we're thinking about, just like we did with sine and cosine. Are there questions? So we're going to look at the cotangent as well. And we're going to focus on those asymptotes for the cotangent. So if I go up to cotangent, here's our cotangent function. I can see cotangent is decreasing because tangent and cotangent are reciprocals. So if tangent increases, cotangent decreases. They're going to do the opposite. Also notice that your asymptotes are at different locations. So our asymptotes are at pi values. So I have an asymptote at negative pi, we have one at 0, and we have one at positive pi. So again, asymptotes at negative pi, 0, and positive pi. So on our graph, at negative pi, we have an asymptote. At 0, we have an asymptote. And at positive pi. And that'll be for every cotangent function. In the middle is our x-intercepts. And then in between the x-intercept and the asymptote, that's our 45-degree angle, our pi over 4 angle. Because cotangent is decreasing, the left side is up at positive 1, and the right side is down at negative 1. So again, you're in the middle of the intercept and the asymptote. So everything is still sectioned equal distant from one to the next. Cotangent is decreasing. That's why the left goes up and the right goes down, opposite of the tangent. So try and connect them, making a curve. Again, I like to start in the center instead of trying to play connect the dots. It makes it a little more curved in the middle there. So we're going to try and graph a tangent function that has a vertical and a horizontal stretch. And we are going to focus on the asymptotes. We'll try and graph those asymptotes, and then in between the asymptotes, we will then try and section it off so that we get those intercepts, and then that point where it's up at 1 or down at negative 1. So our first function is y equals negative 3 times the tangent of 2x. This still has an a value, and that a value is negative 3. However, there is no actual amplitude. So that's the part where, yes, there's an a value, and yes, that a value is going to do something to the graph. But the amplitude is the vertical stretch, and it stretches to infinity. So there is no actual amplitude. The b value is 2. That b value is how we find the period. That doesn't change. What is the period of a tangent function? So think from yesterday. Peter, what's the period of a tangent function?
Would it just be pi?
It is just pi. So the period for tangent is pi over b instead of being 2 pi over b. So to find this period, it's going to be pi over 2. This is going to be the distance between my two asymptotes. So if I look at the one we just did, the distance between the two asymptotes is pi, from negative pi over 2 to positive pi over 2, or from pi over 2 to pi over 3 pi over 2. So now that distance is going to be pi over 2. So we're condensing the graph. So this is a horizontal shrink of the graph. The last thing that we're going to list here, there's not a C value. So a regular tangent graph would say A tangent bx minus c plus d. That's going to be what a tangent function should look like if it has all the letters that we've talked about. We are going to find or calculate our new asymptotes. And define those asymptotes, so this would be the new part for tangent. You're going to take whatever is after the tangent. So that bx minus c, which is this part right here, or all of this. And you're going to set that equal to where the original asymptote was supposed to be located. Well, if I look up above, one asymptote is supposed to be at negative 3 pi over 2. So I would set that equal to negative 3 pi over 2. I would do that again for the next asymptote at negative pi over 2. Again at pi over 2. And finally at 3 pi over 2. You're going to see a pattern. But to calculate the new asymptotes, because everything is based off of the asymptotes in the tangent and cotangent, you need to take whatever is after the tangent or the cotangent function and set that equal to the original asymptotes, because that then gives me where they shift or how they stretch. So in this case, I have 2x after tangent. That is my bx minus c. So I'm going to take that 2x and set it equal to negative 3 pi over 2. And then you're going to solve for x, because that gives me the new location of my asymptote. So Darby, how could I solve for x here?
Would you just divide the 2 and
Yeah.
to get x by itself?
And if I divide by 2 and I have a fraction on the other side, I could really do what instead of divide by 2? Dividing by 2 is the same thing as multiplying by 1/2. So to get x by itself, we divide by 2, or I can just multiply by 1/2. So Darby, where would our asymptote be?
It would be at 3 pi over 4.
Yeah. So now that's the new location of my asymptote. It was at negative 3 pi over 2, but because of this period changing, my asymptote is going to change as well, because the period is shrinking. So my asymptote has to change to correlate with that. So if you continue to do this, look at the next asymptote. So that's my first one. My second one was supposed to be at negative pi over 2. If I follow the same method, I end up with my new asymptote at negative pi over 4. So here's my second asymptote. And you can see that there's definitely a pattern. So once you see that pattern, you can then find the location of your new asymptotes. So I'm going to have one at negative 3 pi over 4, one at negative pi over 4, at positive pi over 4, and then at positive 3 pi over 4. So that would be the change that is happening with our graph. The location of the asymptotes are going to change. Questions on that? So when we go to label our graph, I'm still going to go over 3 blocks, just like I did up here. But instead of saying 3 blocks is pi over 2, now 3 blocks is going to be pi over 4, whatever that asymptote is. So I'm going to go over 3 blocks, and now that value is pi over 4. Very similar to how we graph sine and cosine. Over 3 more. Over 3 more. So don't forget that in between pi over 4 and 3 pi over 4 is pi over 2. So I'm counting by pi over 4. So I have pi over 4, 2 pi over 4, 3 pi over 4. You don't have to go beyond your asymptotes. On the other side, I have negative pi over 4, negative 2 pi over 4, which is negative pi over 2, and then negative 3 pi over 4. We do have an A value of negative 3, so I'm just going to count up 3 blocks and call that 1, because that number still does affect our graph. Or count down 3. So here would be the labeling of the graph. So we're labeling the graph, still counting by the same increment. Because we have pi over 4 values, we counted by pi over 4. So the next thing would be to place those asymptotes, the locations that we just found the asymptotes, place those on your graph. Sorry, this is a 4 down here. So we found a new asymptote to be negative 3 pi over 4, negative pi over 4, positive pi over 4, and then 3 pi over 4. Caden, what goes in the middle of every pair of asymptotes?
A point.
Yeah, the point, the x-intercept. So the x-intercept is in the middle of every pair of asymptotes. The direct middle, so at negative pi over 2, at 0, at pi over 2. And then the last thing, we're going to go directly in the middle of the intercept and the asymptote. And we are going to graph one more point to the left and to the right of the intercept. That point corresponds with the fact that tangent at any pi over 4 value is 1 or negative 1. And if I look at this graph, I can see that this graph is an increasing tangent graph. And to the right, I have a point at positive 1. To the left, I have a point at negative 1. If I go down to my graph that we're trying to look at here, there is a negative 3 in front of tangent. So that means that that point that was originally up at 1, I need to multiply that by negative 3. So it's no longer up at 1, but it's down at negative 3. That's what the A value does to the graph. So originally it was up at 1, but I multiply that by negative 3, and now it's down at negative 3. So again, originally I had a point down at negative 1, but I have to multiply that by negative 3, and now I have a point up at positive 3. So I'm going to mimic that same set of points. On the left, I go up, and on the right, we end up going down. And this is because the A value is negative. So you have to think, what did the original graph do? Where was the original point? And I need to multiply that point by A. And then as best as you can, connect, trying to make it be a curve. It's really hard because it's a stretch all the way up there. So stretch up, stretch down. Are there questions? So we found the asymptotes. That was the most important part. We labeled the graph based off of the asymptote. So we're counting by pi over 4. The intercept goes in the middle of the pair of asymptotes. And then we plot 2 more points in the middle of the intercept and the asymptote. Based off of the original function, we multiply that point by A. Questions? So we're going to graph the cotangent function. We'll work through this one a little quicker. I'm looking at my time and I'm thinking, boy, I only have 5 minutes left, so I'm going to have to talk quick. So we're going to do the same exact steps. Starting with A, that number is 2. But the amplitude is still none. Don't get tricked there. Just because the A value is there, that gives me the vertical stretch of the graph, but there is not an amplitude because it stretches forever. The B value is 1/3. So that means my period is pi divided by 1/3. Well, that becomes 3 pi. And then we need to find the asymptotes. So cotangent A, cotangent bx minus c plus d. So if I look at my original asymptotes for cotangent, they're at all the pi values. So they're at negative pi, 0, and positive pi. So to find the asymptotes, negative pi, 0, and positive pi. So whatever's after cotangent is what you set equal to those asymptotes. So x over 3 is equal to negative pi. It's equal to 0. And it's equal to pi. And then if I multiply by 3 to solve for x, we then find our new asymptotes. So you can count by pi in this problem because it has values of pi, negative 3 pi, 0, positive 3 pi. If I was graphing sine or cosine, I would do the same thing, kind of looking at my numbers, deciding what to count by. Well, they should correlate directly with the asymptotes. Do you have an iPad? Yes. So graph is labeled. I'm going to go on the x-axis again. Plot my asymptotes. I already found those asymptotes, so we did the hard part, finding them. You have an asymptote at negative 3 pi. We have one at 0, and we have one at positive 3 pi. Now, here's where it's a little tricky. Directly in the middle of 0 and negative 3 pi, that's where our intercept is located. So in the middle of 0 and 3 pi should be my intercept. In the middle of 0 and negative 3 pi should be my intercept. And then in the middle of your intercept and asymptote is going to be where your other point remains or lies. And that value needs to be multiplied by 2. So if I look up at cotangent, cotangent originally was up on the left at positive 1. So it's going to go up on the left. Instead of at positive 1, it's going to go up to positive 2. All right, so connect these. Cotangent is a decreasing function. Again, these points I'm placing in the middle of my intercept and asymptote. So I am out of time for today. You have a few problems that you're asked to graph. Remember to use your asymptotes to help you graph. Everything is dependent upon them. Does anybody have questions? So please make sure